Hello and welcome to Submodule 2.1. This is the first submodule in Module 2 on AC analysis. Up to now, we've been talking about DC analysis, where we assume that the current is constant. But now we're going to look at the case when the currents and voltages are changing as a function of time. This requires for us to introduce two new types of devices. Up to now, we have been only looking at sources, and in terms of passive devices, we have been looking at resistors, which is a type of device that converts energy to heat. It converts the energy of the current and the voltage to heat dissipated through its body. The two devices that we're going to look at are energy storage devices. One is going to be the capacitor and the other the inductor. And in this submodule, we're going to look at the characteristics of each. So we're going to see how to use the models for inductors and capacitors. What are the equations that define their characteristics in terms of voltage, current, and power, and also be able to calculate the energy. We said that these devices store energy. Specifically, the capacitor stores energy in an electric field, and the inductor stores energy in a magnetic field. Um, we're going to see by examining the equations that relate current and voltages what this means for the rate of change or for the change characteristics of these quantities. We're also going to be able to define how the inductors and the capacitors behave in the presence of DC sources, as well as how to combine them in series and parallel connections. So here we have a physical model of a capacitor. One way to look at a capacitor is if we have two conducting plates, two electrodes, separated by a dielectric with certain thickness, we're going to form a capacitive connection. A dielectric is essentially an insulator. And we're going to see that for a capacitor, the main characteristic of it is that it stores charge. It stores electrical charge and therefore energy in that electrical field that is going to be formed inside of it. These are pictures of several capacitors. The physical size of the capacitor is really directly related to the amount of charge that they can store. So let's look at the capacitor relationships. The capacitor is going to store charge, and the amount of charge that the capacitor can store is directly proportional to the voltage across it, the voltage with which we are forcing that charge, that current, into the capacitor, into the body and the cavity of the capacitor, and the physical characteristic of the capacitor, of the device, which you're going to call capacitance. If we take the derivative of both sides, the charge and the right hand side, then we can recall that the rate of change of charge with respect to time is the current. So when we take the derivative of both sides with respect to time, we have that the current in the capacitor is equal to the capacitance times the rate of change of the voltage. This is a very important relationship for the capacitor because it's going to, for example, it's going to tell us how it behaves in the presence of DC sources. For example, if we have a DC source, a voltage source that is not changing with respect to time, then this derivative will be zero. and the current through the capacitor will be 0. Therefore, in the presence of DC sources, the capacitor will act as an open source. The other characteristic or the other consequence of this equation is that we know that this derivative has to be finite. This derivative has to be finite. And what that means is that the voltage cannot change instantaneously across the capacitor. If the voltage changes very quickly, although it can never change instantaneously, the current will be very, very high because it's directly related to the rate of change of the voltage across the capacitor. So we can separate the voltage and the current in this fashion, and then we can integrate both sides, and we can get that the voltage across the capacitor is 1 over the capacitance times the integral of the current. And if we know that the voltage at certain time zero is equal to a certain value, then we can say that the voltage across the capacitor is that initial value times 1 over the capacitance and the integral of the current from the time zero when we started measuring and observing that current to certain time t. The relationships for power in the capacitor are similar to a resistor, is simply the product of the voltage and the current. Is the product of the voltage expression times the current expression will give us the time expression for the power. Now, recalling that the current is the capacitance times the derivative of the voltage, we have that the power related to the energy stored in the capacitor is equal to the capacitance times the voltage expression times the derivative of the voltage. We can also integrate that power expression, and we know that energy is the integral of the power, so we can integrate that power expression and we get the following expression all the way here to the right. And if we simplify it and carry over the integral with limits of v of t, then this simplifies to this expression that says that the energy stored in a capacitor is equal to 1/2 the capacitance times the voltage square. So that another summary expression for the capacitor, the energy stored in a capacitor in joules. If we recall that the charge that a capacitor can store is equal to the capacitance times the voltage, another expression for the energy stored in the capacitor is 1/2 the charge square divided by C. Now let's look at inductors. Inductor comes in many shapes. Here are a couple of shapes. The linear shape, where we have some type of magnetic permeable material like iron or graphite with a wire that is insulated from the core wrapped around that core. So this would be a linear type inductor. This would be a toroidal type inductor. And we're going to have magnetic flux lines that flow through that core, whether it is this way in the linear core or inside the donut-shaped core in the toroidal type of inductor. So inductors are devices that store energy in a magnetic field. So these are some of the inductors, shapes, and sizes. So let's look at the relationships for the inductor. So if we have a current, we know from physics that if we have a current run through a conductor, there is going to be a magnetic field generated. So if we have that magnetic field generated due to a current through an inductor with certain inductance that is the characteristic of the device, that is going to generate certain magnetic flux. And we know that the rate of change of the magnetic flux with respect to time is equal to a voltage. Therefore, if we take the derivative of both sides of this equation, we have this expression, which gives us a very important expression, the characteristic equation of the inductor. The voltage induced across an inductor is directly proportional to the inductance, a characteristic of the inductor, times the rate of change of the current. So what are some of the consequences of this equation? Well, what happens in the presence of DC sources? We can see that if the current is not changing, if we have a DC, if we have DC sources in the circuit, then this derivative is going to be zero and the voltage across the inductor is going to be zero. What that means is that for DC sources, the inductor is going to act as a wire or a short. Also, we cannot have this derivative needs to be finite, and we cannot have an instantaneous change of current in an inductor. So if that happens, the inductor is going to oppose that change by developing a very high voltage across it. So let's now separate the current and the voltage in this fashion from this equation and integrate both sides, and we can get the current in the inductor as 1 over L, the inductance, times the integral of the voltage. If we know the current that was flowing through the inductor at time 0, we can know that the current at any given time is going to be that initial current plus the integral of the voltage from that time at which we started observing the voltage here, that integral, times 1 over L. Again, for the inductor, power is also voltage times current. So we can do this similar operations as we did with the capacitor, and recall that the voltage is equal to the inductance times the derivative of the current. And we have that the power is equal to the inductance times the current times the derivative of the current. Energy is also important in an inductor. How much energy is an inductor storing? That is the integral of the power expression. So we can integrate from minus infinity to time t, the power expression, and we get this expression all the way to the right. We can simplify that, and similarly we get a very nice closed expression for the energy stored for an inductor, which is this one over here. So the energy stored in an inductor is 1/2 the inductance times the current square in joules. Remember that the magnetic flux is equal to the inductance times the current, and if we substitute that, we can also see that the energy stored in an inductor, another form of looking at it, is 1/2 the magnetic flux square divided by the inductance. Now let's look at how we can combine series capacitors into a single equivalent capacitor. If we have this situation where we have any number of capacitors connected in series, we can come up with an equivalent capacitance C sub S. If we use Kirchhoff's voltage law and we write the sum of the voltages around those capacitors connected in series, we can say that each voltage is equal to 1 over that individual capacitance times the integral of the current plus any type of initial voltage that we had stored in the capacitor. Therefore, if we factor out the integral, which is the same as the voltage on this side, we come up with the fact that 1 over the total capacitance is equal to the sum of the reciprocal of the individual capacitances. So one way to remember this is that capacitors in series are combined like resistors in parallel. Now let's look at the parallel combination of capacitors. Again, we have any number of capacitors connected in parallel, and we want to know what is the total capacitance equivalent of that network. For this, we're going to write a Kirchhoff's current equation, and we're going to say that the total current is equal to the sum of the currents in each branch, in each parallel branch with the capacitor. And we know that each of the currents is going to be the capacitance times the derivative of the voltage, and we know that the voltage across all capacitors is the same because they are connected in parallel. Then if we factor out that current, we have that the parallel combination of the capacitor is equal to just the sum of the individual capacitances. So we can remember this as follows, that capacitors in parallel combine as resistors in series. Now let's look at the combination of inductors in series. Again, we have any number of inductors connected in series, and we want to know how to combine them into a total equivalent inductor. For that, again, we're going to write Kirchhoff's voltage law equation. And we know that the individual voltages are the individual inductances times the derivative of the current, which is the same for all the inductors because they are connected in series. And then if we factor out that current, we know that the total inductance is simply the sum of the individual inductors. And finally, for the parallel inductors, the total inductance is derived by, again, writing a Kirchhoff's current law equation for all the parallel branches. We know that the total current is equal to the individual currents in the branches. And we know that a particular current is 1 over the particular inductance times the voltage plus any initial current that we had flowing through the inductor at any given time. And then if we factor out the current, which is the integral of the voltage, and also separate the initial current through the inductors, we have the expression that 1 over the equivalent inductance is equal to the sum of the reciprocal of the individual inductances. So inductors, they combine just like resistors. So for series, they simply add, and for parallel, the combination is the reciprocal of the sum of the reciprocals. Keeping in mind that for inductors as well as capacitors, in series you have to account for any initial energy stored in the device. In the case of inductors, it would be any initial currents in the inductors. In the case of the capacitors, would be any initial voltages in the capacitors. And this concludes this module. So we looked at all the equations and relationships for inductors and capacitors that relate voltage, current, power, and energy. We looked at how these devices, the capacitors and the inductors, behave in the presence of DC sources, and we also took a look at how to combine them in series and parallel, and actually we're able to derive that using Kirchhoff's laws.